finally, I'm sitting in my combination shack and home office. I didn't have to shave because they canceled classes at the school I teach in. And in front of me is a beverage in a brown bottle known to you old-timers as 807s. This wouldn't have been permitted in the building you normally hold meetings, and if you don't know what an 807 is, I'll give you one clue. It says Miller on the front of the bottle. There's one large difference between presenting this way and doing it in person. In person, I can look around and see if anyone's puzzled, and if they see somebody who's puzzled, give a better explanation. In the classroom, I can look around and see if anyone's asleep. What I used to do years ago in the classroom was take a vacuum tube, you remember those, put it in a paper bag and throw it against the wall. The noise would generally wake a student up. Today you're not allowed to do that sort of thing, so of course I use my PC to play a MP3 or something. You know, the problem we have in school, as you might guess, is cell phones and texting. The students used to go out when their cell phones buzzed as though they needed the restrooms. You know, after all, it is a college. Today they don't go out, they text covertly at their seats. What I tell them is nobody ever looks down at their crotch and laughs unless they're texting. That usually cures it. Meeting full. Well, that's interesting. In this trial version, you're only allowed 26 attendees, and we have 26 attendees. Well, let me shut that off. I guess there's no choice. Sorry about that, John. We didn't discover that.
Yeah, well.
All right, I guess any latecomers are here, so let's begin. I do ask if you have any questions, just speak up, either right away or at the end. Otherwise, I won't know you need more information. Someone was not allowed. That's okay. Well, I guess that's why you have to pay for this. Anyway, if you can't get through using your microphone, I'm monitoring my mailbox. The email address is pdanzer, I'll spell that, Papa, Delta, Alpha, November, Zulu, Echo, Romeo, at optonline.net. And if you can't get through with the microphone, send me an email, and it should pop up on the iPad here. Anyway, tonight... I'm sorry, just want something, John? Okay, tonight the...
No, it wasn't me, but there is something. Hang on for a second. Well, there's also the chat session that people can do right below where you turn off your microphone. You can send little messages.
Oh, okay. I didn't even try that. All right, I guess we can try that too. This is an interesting situation. We'll see what happens. Anyway, the topic tonight is oscilloscopes. A little bit of yesterday, a lot of today. Comparisons of analog and digital, big ones and small ones, expensive ones and inexpensive ones. And there's a lot of applications for a scope, some of them which are a little bit surprising. So I'd like to start off with one that perhaps you're not expecting. The FCC says you can run as much as 1500 watts PEP. If we were in a room, I'd ask those of you who know how much PEP you're running to raise your hands. The answer is probably the very few of you don't. You know, in the old days, to get your power per FCC, you take the voltage on the final stage, multiply it by the current, and that was the 1 kilowatt input. For PEP on sideband, it's a little bit different. So let's take a look and see what that's like. Here's a typical sideband picture off a scope. Incidentally, as you'll notice a little bit later, let's see, where's my mouse? This happens to be an electronic scope. More of this later. Anyway, the first thing you want to do to know your PEP is measure the peak-to-peak voltage when your transmitter is connected into a 50 ohm load. So you simply take your transmitter, to get from V-peak to RMS. For calculating power, you multiply V-peak by 0.707. finally, power equals V squared over R, where V is in RMS. So the RMS voltage squared divided by the resistance 50. Now, if you don't like equations, here's a graph. And if you notice 1500 watts PEP, you would get a peak-to-peak voltage of something slightly under 800 volts. Now, if you want to do this, I give you fair warning, don't blow up your probe. Most of today's probes are limited to 20 volts, which means you have to put in a resistive divider. But this is one application for a scope most people don't recognize and don't use. Another very simple application is an old favorite, a diode tester. As you can see, the circuit is kind of simple. You got the diodes you're going to test, a couple of resistors. You go into the horizontal or vertical channels, and you put on a filament transformer. You remember those, 5 volts AC, and you get an output. Flat line means it's open. Shorted, you're going to get a diagonal. A good diode will give you this bend where this is the point where the diode starts to conduct. So it's just another simple use in a scope that many people use. Incidentally, if you want to test a transistor, the same thing goes for trying the base emitter junction and the base collector junction. Each of those will appear as a diode. All right, now let's look at a couple of scopes. A lot of us, including myself, love these guys. There was a series of scopes put out by Tektronix, 535, 545, 585, big, heavy. You needed a cart, or if you wanted to carry it, you needed 2 men on a pony, and hot. These days, you can actually buy them pretty inexpensively at a lot of handfests. There is one little problem. Look at my cursor. See these glass things known as tubes? These things need replacing. Also, you have to calibrate this thing because it's mainly analog, and an analog scope needs periodic replacing. If you go back to the front end, the previous picture, if that was a scope that came from a company, you'd probably find a little calibration tag that says this thing was calibrated last in 1962. So you know if you buy this thing, you're going to have a little bit of work to do to calibrate it. Now, if I was there in person, I'd whip this guy out. This happens to be a scope that I own. 2 inches by 8 inches by 7 inches. It has 1.5 pounds. How does it work? It's got 2 channels, and in the back is a connection to the USB, and everything else shows up on the screen. This is very typical of a relatively inexpensive scope that plugs into your PC. Before there were CRTs, there was an interesting type of scope, and it was basically a roll of paper, sensitized paper, and what was then a meter with a pen. And all that would happen is this paper would roll past the pen, and of course the larger the deflection, the larger the voltage that was applied to this meter, and you could record the voltage. Now, as you might guess, the bandwidth, the frequencies this thing worked at, were relatively low. But now we're talking about the 1800s, late 1800s, so we're not talking about using a couple of megahertz. In fact, I'm not sure megahertz existed. Yeah, I know, they were called megacycles, but that's another story. All right, fast forward, 1937. You like this from National? It, by the way, is a perfectly functional scope with a very small tube. But after the Second World War, they got a little more sophisticated. And if you look carefully at the controls, you've got almost everything you need for a modern scope. This was the big transition to scopes. But the best one comes next. Here we go. Again, I wish we were in the same room and see how many of you guys remember this one. This was Heath. Heath went from building airplane kits to building oscilloscopes. All of the parts were surplus. In fact, for a while, they sold the scope kit, and you'd have to buy the tube separately. I think the tube was all of about $5, and it was a 5-inch tube left over from World War II. In fact, all of Heath's parts were left over from World War II. I'm starting to feel real bad because we had about 10 beep-beeps there. The people who can't get in here. This is something that we did not anticipate, John.
Yeah, I sent out an email to both Gene Arc and Sarah explaining what happened there. This is our first try at doing something like this. We'll learn from it.
Well, this is a learning experience and kind of interesting.
Yeah.
Now, the one I really like, because the ARRL handed me this one. I didn't even have an iPad, so they gave me an iPad for a couple of weeks, and this is the scope. Now, I don't know how many of you are familiar with a 5-inch iPad, but this is it. This is the scope. Look carefully. Dual channel analog and 4-channel digital. These are all the controls. And this was menu driven, which means if you were carrying an iPad, or by the way, an iPhone, in your pocket, this little guy was all you need as a scope. Yes, the frequency response was not the greatest in the world, but it worked really well. I had it here for a couple of weeks, tested it, and it was a nice little scope. All right, so now let's look at scopes in general. Every scope, analog or digital, looks kind of like this. You've got the vertical circuits with an input. You've got a display. You've got something to synchronize the display. And then you can take sync either externally or from the vertical circuits. So analog or digital, this is what they all look like. Pardon me while I do a little bookkeeping, but John, I'll ask you again, does this thing show up on your screen? Or you can't see what I'm pointing at?
You say this thing,
yeah. Are you seeing the full title?
I'm seeing the full title. Every scope, analog and digital.
Okay, on my screen, part of it is blotted out by a control panel. I was just curious, that's all. Okay, so what does the front end look like? Well, now it gets interesting. If you have 2 channels, you have 2 input amplifiers. Usually you select AC, DC, or ground. AC, DC, or ground on both.
Tom Agustin. Mute your microphone, Tom. Tom Agustin, mute your microphone. Go ahead, Paul.
Okay. So we have 2 separate channels and 2 inputs. This ground gives you a reference when you're doing a measuring. And usually you can select A alone, B alone, alternate, one or the other, and chopped. Now people get into trouble with alternate, of course, because they think the 2 displays are synchronized, but they're not. First you're looking at this, then you're looking at this, then you're looking at this, then you're looking at this. That's what alternate means. Chopped means you take a little piece of this and a little piece of this, a little piece of this and a little piece of this. So they are synchronized. Now when you go digital, you got another story. The front end is about the same. You probably have some sort of input amplifier. But following that right away is an A to D converter. Converts the analog signal here to a digital signal. In order to save money, quite often the manufacturer will use a single A to D converter. Take these 2 guys, put it into a switch, and run to one A to D converter. So right away you can see that the performance of a digital scope depends to a good extent on how fast and how accurate these analog to digital converters are. Fortunately today, if you're willing to pay the money, they are quite accurate and they are quite fast. In front of it is a probe. Now this is another place where people get into a lot of trouble. The probe plus the connecting cable is nothing more than a network. And a network can usually be synthesized with a resistor, an inductor, a capacitor, another resistor, and here's the shield. In other words, it's frequency sensitive. Therefore, you've got a screw on the probe to something called compensation. Usually you have a square wave built into the scope that you can adjust. Now caution, there's no compensation on most probes when they're set to the ×1 scale. When they're set to the ×10 scale, there's compensation, because in the ×10 scale, there's additional resistors, which now make that cable look way different. What you want to see on a square wave is something that looks like, surprise, a square wave. If the compensation is set the wrong way, this is what your square wave looks like, so everything that you're looking at is going to be distorted. On the other hand, if the compensation is set the wrong way the other way, it's going to be distorted again. Now, if you look carefully, you might notice that this is also being seen on an electronic scope. In fact, this particular one happens to be a software scope that we'll talk about in a little while. There's also all sorts of other probes that are very interesting. You can also get a current probe. Current probe is nothing but two pieces of steel and a coil. It's got a notch. You put the wire that you want to measure the current, and this is only for AC current, through here. Close this so you now have a full magnetic path that goes this way, and this coil picks up the voltage generated by the magnetic path. So you can now see the waveform on the current going through the wire and stuck through this notch. Now let's look at the block diagram a little more carefully. This is a composite. It's a composite of both digital and analog. You've got the standard input vertical system that we looked at before. And then these two little blocks represent the A to D converters if you're in a digital system. Usually, there's some sort of feedback to this to make sure that you stay absolutely linear. In the digital scopes, this goes into a math processor. In all cases, it's going to go down into the synchronization circuits. The synchronization circuits can either give you normal synchronization or delay, and we'll look at that in a minute. And then you have the horizontal processor sweep circuits. Now the reason it's called horizontal processor and sweep circuits is now it's way, way different for the digital and for the analog. And now you get your sweep. The reason I'm pausing is my cursor keeps disappearing. Back into the video processor. And notice for the digital scope, you have something called a memory. And I'm not using the words here CRT, I'm using the word display. Now the vertical section, again, consists of the vertical, where you get channel A and B in, selecting whether you're A, B, alternate or chopped, A to D converters for a digital scope, the vertical processor, and look at this, to a math processor. This is where it gets really, really interesting. Now the controls are the same. Whether you're talking about the old Tektronix scope that we had on the pictures before, or you're talking about the newer scopes. That's interesting, my cursor keeps disappearing. Where you're talking about the newer scopes, where the controls are either all or partially on the screen, you're going to have a position for both A and B channel. You're going to have a voltage selection for the vertical scale. You've got vertical calibrate, and you've got to be real careful about this one. And usually a times 10 position, which will take the vertical scale and multiply it by 10. Now the reason you've got to be real careful on this is if you look carefully at the controls on the old scopes, they always had a little dot. And you had to turn these pots to the dot end where it clicks in so the calibration held. Otherwise, these calibrations were variable. So you'd think you're on, for example, 10 volts per centimeter, but you have the pot turned down halfway, so you're in some indeterminate position. With the newer scopes, of course, this isn't really possible. Now, here's the picture you've been waiting for. CRTs. For, what, 50, no. If I go back to the original ones, almost 100 years, we've had CRTs of one sort or another. And everything was analog. The positioning on the screen, you're well aware of, use some deflection plates vertically, and this is the deflection plates horizontally. And it shot out electrons, you had a phosphor screen, everything that you ever read. The interesting thing is, now the new scopes don't have CRTs. So what are you going to do? Well, first of all, let's look at the analog sweep. The analog sweep says I put a voltage on the horizontal plates. If I started down here at a negative thing and I'm off on the left, as I increase this voltage up towards the positive, I'm going off to the right. And then the scope itself does a retrace down to here. Then it repeats the whole thing. But that's for an analog scope. And perhaps, boy, that makes about 20 of those beeps. That's for an analog scope. But we don't have a CRT, and we don't have this sort of situation on the newer scopes. So what do we have? Well, first we go back and look at expanded sweeps. When you take a sweep and you trigger it, it puts this on the screen to move it horizontally. Many of the scopes have something called a bug, where you can set up a delay and put that bug there. You can then expand the piece of the trace around that bug. Now this is in the analog world. What I'm leading up to is how you do this in the digital world. For example, in this particular one, if we have a bunch of dots, and you're looking at your output waveform on CW, and you want to see what this little transition looks like, you can put the bug right on the edge of this screen, and then you can look at the actual waveform as you start down. Digital. Way different story. Now, on the screen, forget about seeing a sweep. I want you to think of memory locations. In this particular case, the memory location on the left side of the screen is memory address 250. To jump back a little bit to, normal computer kind of stuff, I just discovered why okay, we found another bug to take care of. Everything in the computer has an address. Your output ports, your mouse, everything in there has an address. And of course, memory has an address too. So these are memory addresses, and we've just faked some numbers to give you some round numbers. Now,
Stanley's big day. Happy birthday, Stanley.
Somebody's talking. All right. There's a stored value stored on each of these. So your A to D converter stores the value of 0 at this memory address. A fraction of a second later, it gets another value, and now you go over to a new memory address. A fraction of a second later, you go over to a new memory address. So what you have is in memory the stored values of the input waveform. So now you don't really have a sweep, but what you do in order to see a display is you read this memory, and 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 so on and so on. And of course the quality of your display depends on how many memory positions you're storing information in. Now at this point, if we were in the same room, I would look around and say, okay, everybody follow me. I can't really do that, so let's hope that you did, or else you'll be asking some questions. Now, input modes. Here's again where it gets really interesting for just about all of them. What can you do with a scope? Well, one input mode, you go to ground. That's obvious. The second one, you're AC coupled. Usually that's selectable to each channel. DC coupled, selectable for each channel. One of the things you can do is inverter channel. Differential. Why would you want to use differential? Well, you guys who are into computers would recognize that if you're looking at some computer data being sent, say, on almost any set of lines, you've got two wires. One wire is not ground. In order to see that waveform, what you have to do is you have to go across the two wires in order to see what's going on. Then, following the old type of scope, you had a high gain preamp, which you have to build into the new ones. And that was not compatible with fast rise time, because the circuits that give you high gain weren't compatible with fast rise time. Now, of course, this all depends on what kind of A to D converters you're using. Dual trace, quite obvious. Then how do you select them? Well, A, B alternate we talked about. One sweep, then the other sweep. Chopped. Look at a little piece, jump down, look at a piece of the other one. A plus B, A minus B. Well, if each one is capable of being inverted, you can add them and subtract them. Now here's where you get to a really big difference between analog and digital. In analog, that had to be done up in the front end. In digital, you keep the A channel and the B channel separate, store them separately, and now you can process and do whatever you want with the two of them. You can change the gain on a channel, you can add them, you can subtract them, and so on. These other parts, of course, depend on the input circuits that you're using. You never had separate digital inputs on the old analog scopes. Now you have separate digital inputs. This has an advantage or a disadvantage. One advantage, of course, is the fact that you can have the separate inputs and you're not going to do it. You can have the analog inputs at the same time. However, usually the digital inputs are limited to digital signals of restricted voltages. It's not surprising to find a scope that can only handle digital voltages of under 10 volts, say 0 to 10 volts defined as ones and zeros, so you can't use anything else for your digital stuff. And finally, and we'll get to this in a minute, you've got scopes that will handle audio only. Now this is what you had. When you had the Tektronix line or any of the fixed scopes, you had preamp, or you had certain things that you could do and you can't do anymore, period. This was a D plugin. You have A minus B, B on one, on the other, and you can't do anything else except this. Notice this sneaky little thing. Here we go into calibration again, and here we go into calibration again. I'm sorry, no, these are grounds. Calibration. This knob, by the way, was the knob on the screw that held it in place. And this is what the front panel of the scope looks like today. You got a channel A and channel B, and this particular one has 4 digital inputs. All of your controls are down here. If you want to change the trigger, step on the trigger. Whoop, I didn't mean to do that. I stepped on the trigger. Let's go. Last view. There we go. You click on the trigger. I clicked on the trigger, by the way, since this isn't a live scope. What I did is change slides. You click on the trigger, that gives you a trigger menu. In the trigger menu, you can keep pushing stuff up and down or doing whatever you want. Settings, pause. Big difference. Again, I wish I was in the same room and I asked the question, how many of you guys ever use the storage scope? Now, for those of you who only have a slight idea what's going on, there was a type of oscilloscope known as a storage scope. It would store your traces on the front screen in the phosphor. So if you were looking for something, a transient, that was wrecking your circuit but only happened in a great while, you had to buy an extremely expensive scope that had storage capability, and that storage capability was typical in the phosphor. What it would do is it would keep that line on the scope and the waveform on the front of the scope until you told it to erase. Well, that was an analog scope. Digital scopes work differently. Digital scopes automatically store the data. So if you wanted to find transients, you just set it up for one sweep. When you trigger it, it's going to take that one sweep, put it into memory, and you won't lose it. In fact, you can now process it. This is a huge advantage for people who are trying to debug hardware and getting transients in there that are wrecking their circuits just every once in a while. Any of you who've been involved in that sort of problem, I think, understand the value. And you get this free and automatic with a digital scope, whether you want it or not. When you get a digital scope, you automatically get a bunch of things. Why? Because the digital scope is nothing more than a front end, a A to D converter, and then you go into a processor, and the processor does the work. So what do you get? You can get a digital bus monitor, which means you go into a differential mode, you can monitor a bus. You can get a digital pattern generator, which means it actually puts out a pattern. Of course, you can't do much scope work with that. You can use the scope as a multi-channel logic analyzer. You can get math functions. You can take the data that you've got and run an FFT, a fast Fourier transform. Exam at the end of this program, can you spell Fourier? Derivatives, integrals, statistics, frequency analysis. You can do all of this in the scope by just picking the data and letting it do it. Network analyzer. Some of them actually supply power for your circuits. Some of them have signal generators. Unfortunately, what the manufacturers often don't tell you is if you want to use the signal generator or the power supply or something, you can't use the scope at the same time. Well, that's the penalty. Spectrum analyzer, those of you who have fairly fancy rigs know what this looks like. And of course, a voltmeter. Now, a little bit of caution. Let's talk about the scope characteristics and bandwidth. And in order to do that, we have to talk about something called Fourier analysis. Bandwidth is not what you think. Fourier analysis says for a repetitive waveform can be synthesized by a number of sine waves of multiples of the frequency. For example, a square wave can be made up of a bunch of multiples of the fundamental frequencies, odd harmonics. Here's a square wave. Here's a sine wave with the same frequency. Here's the square wave superimposed on the sine wave of the same frequency plus a sine wave of 3 times the frequency. Here we've added to this a sine wave of 5 times the frequency. Here we've added to that a sine wave of the 7 times the frequency. So you can see as you increase the number of sine waves, you get better and better to this. Well, what does that mean? That means if you buy a scope with a limited bandwidth, and we'll talk about this in a second on software scopes, and suppose it says the bandwidth on this scope, because it's an audio-only scope, is 20 kilohertz. So you say, okay, I can see stuff up to 20 kilohertz. The answer is no. You can see sine waves up to 20 kilohertz, but a 20 kilohertz square wave consists of 20 kilohertz sine wave plus 3 times 20 is 60 kilohertz plus 5 times 20 and so on. You will not get a square wave because you're bandwidth limited. The other thing is on bandwidth is usually specified as the 3 dB point down. That's nice. Here's 3 different scopes. They are all at the same bandwidth number, 3 dB down. But look at scope A. It starts to fall off over here, but actually gets better over here. Scope B falls off here, is over here, and scope C falls off here. So the answer is a single number on bandwidth is not the only measure. Now the other thing that gets interesting with these scopes is sampling rate. Here is a fast waveform. As you can see, it's a square wave. This may be somebody's transmitter who's not doing too well on transmitting dots. And you see what it actually looks like on an analog scope. On a digital scope, sampling takes a bunch of pieces. And look what you miss. You miss a lot of this, and you don't realize what the actual thing is. And the sampling rate tells you how many samples per second that you can actually get. There is a way around it, and it's kind of interesting. If it is a repetitive waveform, here's what they do. Now again, remember it has to be a repetitive waveform. Here's the horizontal time axis. First time through, they synchronize the scope to take a sample and convert it, the A to D converter here, 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 and here. That's at the maximum sampling rate. Now what they do is they go back and change the trigger point by a little bit. So instead of triggering to sample here, it samples here, samples here, samples here, and would sample out here. Then they go back and move the sync point a little bit more. So now in the space where I had 2 samples, I now have 6 samples where I only had 1 sample before. So I can actually see that the previous waveform with more samples if it is a repetitive waveform. If it's not a repetitive waveform, this little trick doesn't work. Okay, to quote from the commercial, where's the beef? The final type of scope, which is absolutely fascinating, especially since it's cheap, is a scope that doesn't have any hardware. You go online and you download it, and it's free. Well, there's a couple of paid ones, but it's free. But before we look at the scope, look at the capabilities. It's got an oscilloscope. You can do XY graphing, measure the frequency. It generates signals, and a bunch of other And this is the panel that lets you pick what function you want to do with it. Here I've picked oscilloscope. And as you can see, it's got 2 channels, and it's got color coding, and this is showing up on my PC. Okay, what's the disadvantage? The disadvantage is that this thing plugs into the line input. Actually, it plugs into the stereo input. Gotta be careful there. The stereo input on your PC. A little jack in the back that says stereo. And each channel goes into one of the stereo inputs. So one of these feeds this green waveform, and this comes out on your PC. The other channel feeds this red waveform through the stereo jack in there. Now, since it's using your sound card, obviously the frequency response is going to be limited by your sound card. Sound cards do a pretty good job these days of sampling, but their maximum frequencies are limited to what? Sound. So you can guess that if you're not using this for audio reasons, it's not really all that useful for RF or that sort of thing. What's the advantage? Hey guys, it's free, and it's a lot of fun. It'll take you 15 minutes to download it, install it, and try it out. What else do you have to do? Well, you got to protect it. So you got to put a couple of diodes up front as limiters. And if anybody wants to try this, I'll be glad to send you the very simple circuit. So that if you put too much voltage into your sound card, remember your connection is into your sound card. That's the probe input. This is all software. The probes go into your sound card. So you have a little protection circuit with a couple of diodes that clip it out if you hit it with too much voltage. If you hit it with too much voltage, you can blow out your sound card, which is not a very desirable situation. Alright, this is the point where I'd ask any questions, but let me just go on further and talk about some of the things you can do with a scope. First of all, you can measure amplitude. That's obvious. With a sweep generator, you can do alignment. You can see the transmitted waveform. You can see the sideband waveform. Where it really comes in handy for you guys who run CW is to see what in the world your key clicks look like. Digital signals you can examine, RF detection with the old-fashioned put a diode in and a capacitor. You can measure time and frequency, and finally you can actually measure frequency against a standard source using something called Lissajous patterns. All in all, the scopes are pretty handy. The price on some of the newer ones, the digital ones, are well below $300, and you've got capabilities there that you couldn't have dreamed of a long time ago. Besides that, those of you who've ever used the old scopes, there's one huge disadvantage. You can pick up the new scopes in one hand. Thank you all. At this point, let's see if we have any questions that I can answer this way. Hello?
Folks, if you want to ask questions, there's that green, or it should be red right now, thing that looks like a microphone on that little GoToMeeting control panel. If you click on it, you'll unmute yourself. You can ask questions.
John, for interesting purposes, I also set this thing to record.
Good, because I think I would like, I'd like to get if you don't mind, I'd like to get a copy of it and put it on our website.
Not at all. Not at all.
So
I just feel bad that so many people got locked out. There must have been another 20 to 25 beings.
Well, some of it was people in and out. What happens frequently with not frequently, but people who are new to GoToMeeting, is they accidentally shut themselves off. You know, they mean to click on something else, and then they've actually clicked themselves out of the meeting, then they come back into the meeting. So I was watching, and it was a lot of it was people who were accidentally dropping out and coming back in. So
okay, I guess you'll get some feedback from the guys and gals.
There's also some commentary going on the side there. Somebody came up with the as you started your discussion, somebody came up with the idea of that software scope, and everybody was saying, no, you can't do it. And then you said, oh yeah, here's how you do that. He was going, I guess it does work. So, so with the software only, we really can't do any RF work, is what you're saying.
Yeah, I mean
The sound card based, I'm sorry.
with the sound card based one, you're limited to what your sound card is. You know, they've got 44 kilohertz sampling rates and all that sort of thing. But you're really down. You know, 15 kilohertz audio is if you want to use it for aligning, checking out the linearity of an amplifier or something,